Europa Foods is thinking about investing £6 million in capital equipment in order to save on labour costs. We need to decide if it's a good investment to make. The £6 million will be paid for in 3 equal instalments. Initially 2 million, then a further payment of 2 million at the end of each of the next 2 years. Their estimated labour cost savings will be £1 million a year, starting at the end of year 3, and we're going to assume that interest rates are going to stay at their current level of 6%. First, let's focus on the costs of the investment. So the cost of the investment is going to be less than £6 million because the payments are staged. We can express it like this. C, the cost, equals 2 plus 2 times 1 over 1.06 plus 2 times 1 over 1.06 squared, recognizing that the amount of money that they'll spend in future years is in current terms somewhat less than 2 million because they don't have to find the money now. This is 2 plus 1.887 plus 1.780, which comes to 5.667 millions. That is the true cost of the investment in the project. Now, the cost savings are estimated at £1 million annually, but only for 10 years. The machinery will eventually wear out. Will it be worth the investment after we've discounted these benefits? Now, since this cash flow is a constant sum, we can use our geometric series formula, A times r to the n minus 1 over r minus 1. But we need to modify it as the cost savings don't begin immediately. A, the £1 million worth of savings, only begins after 2 years. This is 1 times 1 over 1.06 squared. So we have 1 million times 1 over 1.06 squared, and then inside the brackets 1 over 1.06 to the n minus 1 minus 1 over 1 over 1.06 minus 1. Moving the term 1 over 1.06 squared inside the bracket will give us 1 million times 1.06 to the 1 minus n minus 1 over 1.06 minus 1.06 squared, and in our case n equals 10. So we've got 1 million times 1 minus 1.06 to the minus 9, because we've only got 10 years, over 1.06 squared minus 1.06. 1.06 to the minus 9 equals 1 over 1.06 to the 9, which is 1 over 1.689, which is 0.592. So we've now got 1 million times 1 minus 0.592 over 0.064, which is 6.375 millions. So we've got a gross present value of 6.375 millions. That is the labour saving costs once we've discounted them. And the capital cost is only 5.667 millions. So the net present value, the gross present value minus the capital cost, is 6.375 minus 5.667 equals 0.708 millions. So to interpret this result, to secure this cash flow of cost savings at 6% interest, we'd need to put 6.375 million into a bank account. But this project will yield those cost savings for 708,000, less than that. So the decision looks quite attractive. It actually looks less attractive because we've ignored savings beyond some cut-off point, in our case 10 years. And if the machinery were to last longer, then the project would be more valuable. But remember that the further into the future the savings are made, they're quite small by the time they've been discounted. So, for example, 1 million saved in 15 years' time is only worth £417,000. So in this case, our conclusion is that the project is worthwhile, and it's worthwhile given the assumptions that we've made. If we change the assumptions, if it costs us more to invest, or if the cash flow savings are less, then we might come to a different conclusion.